Welcome back to the deep dive. Today we are going to try to tackle a question that might seem, at first at least, like it lives purely in the abstract world of mathematics. But I gotta tell you, for anyone who's grappling with the fundamental nature of reality, and I know a lot of you philosophers out there, this is a profound mystery, and it's one that's been around for quite a while. And that is the mystery of the continuum hypothesis.
That's right. For over a century, this question, it sounds straightforward, at least on the surface, about the very fabric of infinity, has really captivated and perplexed, I'd say, some of the most brilliant minds in mathematics. And it's led to some really unexpected twists, turns, and sort of philosophical forks in the road.
Okay, so let's unpack this a little bit. When we talk about the continuum hypothesis, what are we actually talking about? What is this thing? Now, you're familiar with different orders of infinity, different sizes of infinity.
Right.
Cantor revolutionized mathematics in the 19th century when he showed that infinity isn't just one size fits all. The infinity of the natural numbers, 1, 2, 3, and so on, is actually smaller than the infinity of the real numbers, those decimals that go on forever, never repeating.
Right. What Cantor discovered was really a hierarchy of infinities, and these different levels of infinity are often denoted using the Hebrew letter aleph with subscripts. So air represents the size, the cardinality of the natural numbers. So, that's what we often call countable infinity. And then the next step up in this hierarchy is air, and so on. And the continuum hypothesis asks a very, very direct question. What is the size of the set of real numbers? Is it precisely air? In other words, is there some intermediate level of infinity that kind of sits nestled in between the countable infinity of the natural numbers and the larger infinity of the real numbers?
And that's basically it. It's a very simple sounding question. But the implications are huge. This isn't just some kind of niche puzzle that mathematicians play with in their ivory towers. The answer to the continuum hypothesis actually has deep, deep implications for our understanding of the structure of mathematical reality. Like, really, the fabric of it. I mean, think about it. If there's another kind of infinity lurking between these two really fundamental sets, it would completely change how we view the infinite.
Yeah, absolutely. And the historical significance of this problem is immense. I mean, Cantor himself, the guy who discovered this whole hierarchy of infinities, he wrestled with this problem, the continuum hypothesis, for decades. He was never able to prove it. He was never able to disprove it. And then David Hilbert, at the turn of the century, the 20th century, he gave his famous list of, the most important open problems in mathematics for the 20th century. And guess what? He put the continuum hypothesis at number one. He recognized its fundamental importance.
And like Cantor, Hilbert was also unable to solve it. I mean, for decades, the continuum hypothesis really stood as a symbol of the limits of our ability to prove things in mathematics. But then came this groundbreaking and in some ways unsettling work of Kurt Gödel and Paul Cohen in the 20th century.
Yeah. What they did, their combined results were really revolutionary. First, in the 1930s, Gödel showed that the continuum hypothesis could not be disproved using the standard axioms of set theory. The standard axioms of set theory are called ZSC. These are kind of the basic rules that most working mathematicians agree on when they're reasoning about sets and how they work. And what Gödel did was he constructed what's called an inner model of set theory. It's like it's a very nice, well-behaved little universe of sets in which the continuum hypothesis actually holds true.
So he said, well, you can't disprove it because, look, here's a world where it's true.
Exactly.
And then a few decades later, Paul Cohen comes along in the 1960s and says, okay, but you also can't prove it.
Right. He kind of provided the other half of the puzzle.
He proved that you can't prove the continuum hypothesis from ZFC either. And the way he did this was he developed this really, really powerful technique called forcing, which allows you to construct what are called outer models, or sometimes called generic extensions of the universe of sets. And in these outer models, you can actually show that the continuum hypothesis is false. So what you have now is the ability to build different but equally consistent mathematical worlds where this fundamental question has a different answer. It's either yes or no, and it's incredible.
Yeah, it's really a remarkable thing. I mean, what Gödel and Cohen together showed is that the continuum hypothesis is independent of the standard axioms of set theory, which means that assuming ZFC itself is consistent, which most mathematicians certainly believe, both continuum hypothesis, CH, and its negation, not CH, are consistent with ZFC. So neither one can be derived or refuted from just the axioms of ZFC alone.
And for you as a philosopher, I mean, this is where it gets really interesting, I think. This independence created kind of a fork in the road for how we think about mathematical truth.
Right.
On the one hand, you had you had the pluralists, people like Cohen himself, and they argued that this independence actually settled the question, like because it showed that it has no definitive answer. It's like, look, we can have perfectly valid, consistent mathematical universes where CH is true, and equally valid ones where it's false. So that's just the nature of it. It's almost like mathematical relativism in a way.
Right. The truth is relative to the world that you're looking at.
Right. And then on the other side of the fork in the road, you have these non-pluralists. And these were people like Gödel himself. And they believed that this independence didn't really settle anything. It just highlighted the limitations of our current axiomatic system, which, again, is ZFC. They said there is a deeper truth out there waiting to be discovered. And what we need are new axioms, new, justifiable principles that would be strong enough to actually settle CH definitively one way or the other. And in fact, Gödel himself speculated that what are called large cardinal axioms, these are axioms which assert the existence of these incredibly large infinite numbers beyond, the ones that we've been talking about, might actually be the key to unlocking this mystery. He believed that the universe of sets was just much richer than what could be described just by these ZFC axioms alone.
And what's really remarkable is that Gödel's program of looking for these new axioms, especially large cardinal axioms, has been surprisingly successful, right? I mean, it has settled many questions which were also shown to be independent of ZFC, but CH itself has remained very resistant to this approach. It's ironic because it's almost as if Gödel pointed us in the right direction but said, but you got to go further.
Yeah, that's a great way to put it. It really, sort of points to exactly the point where that approach, at least in its standard form, reaches its limits.
Right. So that brings us to what we want to do in this deep dive,
right?
Especially with you as a philosopher listening. What we're going to do is we're going to explore some of the major attempts to settle the continuum hypothesis that go beyond the standard framework of ZFC.
Right.
And we're going to focus on the philosophical implications of these different attempts. So we're going to look at both sides. We're going to look at the arguments for believing that CH has a definitive answer, waiting out there to be found. And we're also going to look at arguments for why it might be inherently undecidable, that its truth value really just depends on which mathematical world you decide to inhabit. Okay, so let's start by diving into sort of the realm of the infinite.
Right. We're going to talk about cardinal arithmetic. Now, you might think if you have infinitely large numbers, adding them, multiplying them would be this incredibly complex, crazy thing to do. But it turns out it's actually really straightforward. It's really simple. For any two infinite cardinal numbers, let's say we call them kappa and lambda, their sum and their product are just equal to whichever one is bigger. So, for example, if you have, one infinity is larger than another, you combine them together, you don't get this even bigger infinity. You just get the bigger one.
Exactly.
So, for example, if we have the infinity of the natural numbers and the infinity of the real numbers, which may or may not be euro, then euro plus euro is just euro.
Right.
And multiplied by euro is also just euro. But when you start to exponentiate, when you start raising one infinity to the power of another, that's when things get much more interesting and significantly more complicated. Right. So this is where Cantor's famous theorem comes into play. What Cantor's theorem tells us is that for any cardinal kappa, 2 kappa is always strictly bigger than kappa. So there's always a larger infinity that can be found in what's called the power set of kappa. So the power set is just the set of all subsets of kappa. Now, of course, we understand 2 cantas when n is just a finite number. But the real profound question here is where does 2 Carinus, which represents the size of the real numbers, fit in this hierarchy of infinities, the Aleph hierarchy? Is it the very next one up, or could it be E, or even further down the line like EO?
Yeah, and so that really is the essence of CH, right? The question is 2 theorem to EO. Now, the generalized continuum hypothesis, which is often abbreviated to TCH, takes this idea one step further. What it says is that for all ordinal numbers, alpha 2na10 my e10 x b10 x bc equals a day r day x b10 x bc. So in other words, if GCH were true, then we would have a complete set of rules for how cardinal exponentiation works across the entire infinite spectrum.
Right.
We would have a really neat and tidy picture.
But as we've discussed, ZFC doesn't settle either CH or GCH. In fact, for quite some time, really, the only sort of significant progress that was made on this question beyond just, Cantor's theorem itself was Koenig's theorem, which tells us that the coffinality of 2 kappa is always strictly greater than kappa. So just for those who aren't familiar with the term coffinality, it's roughly the smallest size of an unbounded subset of a cardinal. So you can kind of think about it as how quickly you can reach that large number by taking smaller steps.
So it's like, the steps leading up to the infinity.
Yeah. Exactly.
Okay. And then we had Easton's theorem, which came in the 1960s, and it really showed how much freedom ZFC allows for in determining the behavior of this continuum function 2 kappa, at least when you're talking about regular cardinals. So regular cardinals are those whose coffinality is equal to themselves. So, AO, AO, and so on. These are all regular cardinals. But Easton's theorem says, look, as long as you have some function, we'll call it f, and it's defined on these regular cardinals, and as long as it satisfies just a few basic intuitive properties, like it's non-decreasing, so as you go up, the function goes up, and f of kappa is always bigger than kappa, and the cofinality of f of kappa is also bigger than kappa, then you can find a model of ZFC where 2 kappa is exactly equal to f of kappa for all of those regular cardinals. So essentially, ZFC doesn't say anything about the continuum function, at least as far as regular cardinals go. It's just wide open. It just gives us these minimal conditions.
So philosophically, this is a remarkable thing. It means that in our standard framework, the question of the size of the continuum is almost entirely open.
Yeah. Yeah, it's a lot of freedom there. So we see this incredible freedom at the level of the regular cardinals. But now let's go to the singular cardinals, right? So these are cardinals whose coffinality is actually less than themselves. So an example of a singular cardinal would be like Aleph. That's the first infinite cardinal after arrow, and so on. Right. So it's the limit of all those Alephs. And its coffinality is actually just omega, which is countable.
Right.
And it's fascinating that when you go to these singular cardinals, the rules seem to change.
Yeah. So at first, mathematicians suspected that maybe it was just as unconstrained at the singular cardinals as it was at the regular cardinals. But then Silver proved this remarkable theorem. Silver's theorem says that if you have a singular cardinal, we can call it n psi by E10 ISB 10xBD, which has uncountable coffinality. And if GCH holds below that cardinal for all the cardinals less than n psi by E10 xB 10xBD, then GCH must hold at n psi by E10 xB 10xBD as well. And this is actually a theorem that's provable in ZFC. You don't need any extra assumptions. What it means is that GCH can't just fail arbitrarily. There are certain dependencies and restrictions that are just inherent in the structure of this hierarchy of infinities.
So it's like the singular cardinals, they actually behave a bit more nicely. It's not just a free-for-all like it was with the regular cardinals. So this result really sparked a lot more interest in the behavior of 2 kappa for singular cardinals. So, for example, Galvin and Hottenall, they proved a bound on 2 ambi 10xBD when ambi by E10x B10xBD is a singular strong limit cardinal, again, of uncountable coffinality. And a strong limit cardinal is just one where for any cardinal alpha less than by 10xb 10xbd, 2 alpha is also less than by 10xb 10xbd. So it's like a strong limit. And then later on, Sheila extended these kinds of results to singular cardinals of countable coffinality. And he even showed that if arrow, that cardinal that we were talking about earlier, is a strong limit cardinal, then 2 arrow has to be less than arrow.
Yeah.
And that's regardless of the size of 2 arrow.
Yeah. Yeah.
So it's like you're putting a bound on it no matter what's happening at the level of the continuum.
Right. Exactly.
So the key takeaway here, I think, especially for this philosophical question about the continuum hypothesis, is that the behavior of this continuum function at regular cardinals where CH lives, right? Because OR is a regular cardinal. It's basically completely undetermined in ZFC.
Right.
But then you go to these singular cardinals and the behavior is much more controlled. So it makes you wonder if maybe we need to go beyond just thinking about ZFC and just the arithmetic of regular cardinals to really understand what's going on with the continuum. Maybe there are deeper principles at play that are kind of hinted at by these constraints at the singular level. Yeah,
that's a really interesting point. It's almost like the laws of arithmetic at the level of infinity are very different depending on what kind of infinity you're working with.
Right. Okay. So another strategy that people have tried to resolve the continuum hypothesis is to focus on what are called definable versions of CH. So the idea here is that maybe if we just restrict our attention to sets of real numbers that we can describe very precisely, then we can get a better handle on the question. So, philosophically, this approach kind of gets at this question of whether our ability to describe a mathematical object, to define it, actually tells us something about its fundamental properties or its existence.
Right. In fact, Cantor himself had some early attempts to tackle CH, and they involved looking at these relatively simple or well-behaved sets of reals. So, for example, there's the Cantor-Bendixson theorem. What this says is that for any closed set of real numbers, a form of CH actually holds. So any infinite closed set is either countable or it has the same size as the continuum. So in that realm, for those kinds of sets, there's no in-between.
Yeah, so there are these sort of special cases where it seems to work out. Okay. Now, it turns out that there are actually three different ways to formulate the continuum hypothesis. But all three of those ways are equivalent if you're assuming just ZFC. So you've got the interpolant version, you've got the well-ordering version, and you've got the surjection version. And these become especially interesting when we start to talk about these definability constraints.
Right. So maybe we should kind of lay out for our listeners what these three versions are.
Yeah, that'd be great.
So the interpolant version of CH says that there is no infinite set of real numbers whose size is strictly between the size of the natural numbers, so year, and the size of the real numbers, so 2 years. So the definable interpolant version would then say, is there any definable set of real numbers? Where definable is taken with respect to some precise notion of definability that we have to specify. Is there any definable set of real numbers whose size is strictly between years and 2 years?
Okay. Yeah, so we're sort of looking at subsets of the real numbers that we can define very precisely. And we're asking, does CH hold in that realm? And it turns out that for certain very restricted notions of definability, so for example, if we just look at closed sets, like in the Cantor-Bendixson theorem, or if we look at what are called EFO sets, these are sets that are kind of low down in this hierarchy of definability that's called the projector hierarchy for those kinds of sets. You can actually prove this definable version of CH just in ZOC. You don't need any extra assumptions. But if you want to go further, if you want to talk about stronger, more inclusive notions of definability, then you often need to invoke stronger assumptions. So you need things like axioms of definable determinacy or large cardinal axioms. And these stronger assumptions can sometimes imply that CH holds for even broader classes of definable sets. So you can go really, really far up this hierarchy. You can even go up to what are called universally bare sets. If you assume the existence of a proper class of what are called wooden cardinals, and these are extremely powerful large cardinal axioms.
Right.
So that's the interpolant version. Now, what about the well-ordering version?
Right. So the well-ordering version of CH says that every well-ordering of the real numbers has order type less than or equal to arrow. So what does it mean to well-order the real numbers? It just means to arrange them in a sequence. So every subset of the real numbers has a least element. And the order type is just a measure of how long that well-ordering is. And so the definable version would say that every definable well-ordering of the reals has order type less than or equal to E. And similar to the interpolant version, stronger foundational assumptions can sometimes give us this conclusion for richer and richer notions of definability.
Okay. And so now the third version, the surjection version, this one is a bit more, I guess, abstract in a way.
Right. So the surjection version says that there's no surjection from the reals onto Oro. So what is a surjection? A surjection is just a function which hits every element in the range. So it's saying that you can't map the real numbers onto this higher cardinal in a way that hits everything. And this is actually equivalent to saying that there's no pre-will ordering of the reals of length Yor. And so the definable surjection version, what it asks is there any definable surjection from the reals to ear? Or equivalently, is there any definable pre-will ordering of the reals of length Yor?
Yeah. Okay, so it's all about these mappings. Can you create these mappings from the real numbers to these higher levels of infinity in a definable way?
Right, and this is actually where things get really interesting, and it's also where I think the philosophical implications might be the most direct. So in this case, axioms of definable determinacy and large cardinals give us upper bounds on how long these definable pre-will orderings can be, and we can even show that the length of these definable pre-will orderings is very closely connected to the strength of the large cardinals that we're assuming. So, for example, if we assume that there are infinitely many wooden cardinals, then that gives us certain upper bounds on how long these definable pre-will orderings can be. And so then the question becomes, can we actually push those bounds down far enough to show that they're always less than arrows? And if we could do that, then we would actually verify this definable version of CH.
Yeah. So the hope there was if we can make these mappings simple enough, then we might be able to prove that they can never reach arrow. So they would have to stop at arrow.
Right. Exactly.
Okay. So there was this program in the 1980s. This was initiated by Matthew Foreman and Menachem Majidor, and they had this very ambitious goal to show that if you assume these large cardinal axioms, then this third version of CH, the surjection version, actually holds for all sets in what's called L. This is the constructible universe, which is a very important inner model of set theory, and even more broadly for what are called universally bare sets. So they were trying to push this definable version of CH really, really far. Their aim was to show that these measures of the complexity of these definable orderings, they're always bounded by arrow, at least when you're assuming these sufficiently strong large cardinals. So that would have been a very strong argument in favor of CH, right? At least in this robust setting with lots of large cardinals. But then Hugh Wooden, he came along in the early 1990s, and he proved something very interesting. He showed that if you assume the non-stationary ideal on EO is what's called saturated, which is a property that you can force to hold. You can create models where this is true, and you can do this if you have large cardinals around. So assuming this non-stationary ideal is saturated and that there's at least one measurable cardinal, which is a pretty large cardinal, then this measure, which is very closely related to these definable pre-will orderings, it's called delta 1, 2, actually equals AO.
Right.
So what that means is that it is possible to have these definable orderings even in the presence of large cardinals, which go all the way up to O's. So they're not bounded by O's.
Right.
So this was kind of a blow to this Foreman-Magidor program.
Right. So, I mean, what it shows is that large cardinals might rule out the first two kinds of definable counterexamples to CH, so the interpolant and the well-ordering versions.
Mm-hmm.
But they don't seem to rule out this third kind, the surjection version.
Yeah. Yeah, so we can't use large cardinals in that straightforward way to get us all the way there.
But of course, this doesn't necessarily mean that they prove that such definable counterexamples exist either.
Right.
It just means we don't know.
We don't know. Yeah, it's fascinating that we have this situation where we have these incredibly powerful axioms, and we're still not able to say yes or no.
Right. And Don Martin, he actually pointed out that there's a really important asymmetry here. If we were to find a definable counterexample to CH, if we were to actually find some definable surjection from the reals onto O, that would actually be a genuine refutation of CH.
Yeah, because that would just show that it's false. Right.
Exactly. But verifying these definable versions, even if we could go all the way up the hierarchy of definability, that would never actually prove the full continuum hypothesis.
Yeah. It's like the definable versions are only useful if they give you a no answer.
Right.
But if they give you a yes answer, then you still don't know.
Yeah.
Okay. Yeah. That's very subtle and interesting. Okay, now this third version, this surjection version, it seemed particularly promising to a lot of people. Because it deals with these sets that they're not considered to be atypical in the way that, for example, sets which have the perfect set property are considered atypical. And these atypical sets are the ones that are often invoked when you're looking at the first two versions of CH.
Right.
So there was this hope that maybe the Foreman-Magidor program, even though it didn't work in its initial form, maybe that would actually lead to a way to find a definable counterexample to CH. That would be huge, right?
Yeah.
And that would really change how we think about the continuum.
Yeah, absolutely. And it's worth pointing out that although Wooden showed that the Foreman-Magidor program in its original form couldn't work, he later on did more work that kind of clarified the situation a little bit more. So he showed that if you assume a proper class of Wooden cardinals and that there is what's called a saturated ideal on AOs, then a different measure, which is similar to this delta 1, 2 measure that we were talking about before, but it's called theta upper L of A comma R. So if you assume these things, then this measure is less than or equal to air, at least for all universally bare sets A. And this is a really subtle result, but what it suggests is that the earlier obstruction that Wooden found, the one which showed that the Foreman-Magidor program couldn't work, maybe that was really due to the peculiarities of trying to force this saturated ideal on AO.
Yeah, so it's like a very specific obstacle, right? It's not like a general thing.
Right.
Okay. So where does all this leave us, with this definable version of CH? Well, it seems like the large cardinals are good if you're looking for a yes answer to the first two versions of CH, like the interpolant and the well-ordering versions. But for this third version, the surjection version, it's still very unclear. And so we still haven't found a way to rule out those definable failures of CH using large cardinals. But we also haven't found a way to prove that they actually exist.
Right.
So it's just it's this really delicate balance. There's even an open question in set theory, which is if you take ZFC and you combine it with this really strong axiom called the axiom of determinacy in L. So this is often abbreviated as Stoneman. It's a very, very strong axiom that actually contradicts the axiom of choice.
Huh.
But you can still have it hold in L.
Right.
So the question is, if you combine ZFC with LDO, does that imply that theta upper L of R's is less than or equal to L? And if it does, then that would actually rule out a definable failure of 2 arrows in that setting, at least in the axiomatic framework. Okay, so this whole exploration of the definable versions of the continuum hypothesis, it's really fascinating, right? It hasn't given us a definitive answer to CH, but it has given us all these really incredible insights into the structure of definable sets of reals. And it's really shown us the power of these large cardinal axioms, and it's also shown us the subtlety of these different formulations of what appears to be the same hypothesis. I mean, from a philosophical standpoint, it really shows you how important it is to pay attention to the specific meaning of your mathematical statements, right? Because you might think these are all the same, but when you start to put in these definability constraints, it turns out that they could have very different truth values.
That's right. It's not just about the statement itself. It's also about the framework in which you're considering it.
Yeah, exactly. Okay, so all this led Wooden down a very interesting path. He started to think about, well, maybe there's a way to actually find a canonical model of set theory where the continuum hypothesis is just false. So he was looking for this model that's in some sense the right model, the most natural model. And he wanted this model to have this property that its fundamental properties actually don't change even when you try to extend it using forcing.
Right. So the motivation for this approach, it really stems from the observation that if you assume large cardinals, sufficiently strong large cardinals, then the theory of second-order arithmetic, which, is just the theory of natural numbers and sets of natural numbers, and even more broadly, the entire theory of L, which we were talking about earlier, the constructible universe.
Yeah.
These things actually exhibit this property called generic absoluteness, or sometimes it's called forcing invariance.
Mm-hmm.
And what that means is that their truth values are the same no matter which forcing extension you go to.
So in other words, if something is true in L, it's not like you can force it to become false.
Right.
And it's remarkable, right? It's like you're finding this stability in the face of all this potential change that forcing could introduce. Yep. So this suggested to Wooden that maybe these large cardinals are pointing us in the right direction. Maybe they're giving us some kind of guide towards a more complete and robust picture of these fundamental areas of mathematics.
Exactly.
And so Wooden, he actually found this very special kind of forcing notion called Pmax, so mx. And this forcing notion has the amazing property that if you take L and you force with mx, you get this model, this L of mx. And this model satisfies all the axioms of ZFC, and it satisfies the negation of CH. So it's a model where CH is false. And the key characteristic of this model is that it has this property of being maximal or saturated. What that means is that it has this tendency to satisfy sentences which are consistent with it via forcing. So if you can imagine some sentence and that sentence could be true in some forcing extension of this model, then it's generally actually true in the model itself. So it's a very, very complete kind of model in a specific technical sense. Okay, so to make this a little more precise, I think it's helpful to talk about how we can organize the universe of sets.
Right.
Because there are a lot of sets. So one way to organize it is using what's called the V alpha hierarchy. And this is just indexed by the ordinals. So you start with VOs, which is the empty set. And then you go to VOs, which is the set.